It's
screen. The full screen.
No, read the notes and then result is like I don't know. So much. I can really
It's like this thing is not like
Yeah. Right. Thank you for coming to this special seminar. We are very happy to have Professor Hitoshi Murayama from Berkeley and KU, and we'll be talking about non-perturbative gauge theories and their applications.
Okay, thank you. So I realized that this is not a standard time for theory seminar here. So thank you for accommodating me. So here's the title: Some Exact Solutions to Non-Perturbative Gauge Theories and Their Applications. And this is the series of work I've been doing last several years. And here's the main point. So there are actually very few methods to study strongly coupled systems like QCD. But we all know the non-perturbative effects are essential to understand dynamics of QCD. So what I'm trying to do is the following. So we first make the gauge theory supersymmetric. And because young people these days don't study supersymmetry, I understand. So I will give you some review on how supersymmetry works in a moment. But anyway, suppose you do that, then it had been known by famous people like Witten and Seiberg that supersymmetric gauge theories can be solved non-perturbatively, exactly, which is great. But it turns out that those solutions don't seem to look like a real world QCD at all. I tell you in what sense they look different from each other in a moment. So it still doesn't tell us much information about the non-supersymmetric QCD we would like to understand. But it turns out that if you break supersymmetry in a specific way, I will explain also how that is done, then all of a sudden the theory starts looking like the real world QCD. So it's like starting with a real cow you were trying to understand. And as we always do, physicists make it a spherical cow. And that's a supersymmetric QCD. But the minute you break supersymmetry just a little bit, then it starts to show all these white features or where the head is, where the tail is. So it starts looking like the real world QCD that you can even start calculating things like the mass spectrum in the theory. And that is still meant to be an exact solutions to non-perturbative gauge theory. And I also make an argument that what you can study pretty close to supersymmetric limit seems to be continuously connected to non-supersymmetric limit, that what you're learning here would be telling you something about what's going on over there. So that is the main idea.
I'm curious about the cow. How do you produce this?
Oh, download it. Yeah. And so here the concrete results I can show you how I can use this technique to demonstrate how non-perturbative QCD actually works. First of all, chiral symmetry breaking is what Nambu proposed a long time ago right here. And that's something we always assume what QCD does, but that's something you can derive using this technique. You can show that Q bar Q condensate is there. You can also show that theory confines when appropriate. And what I mean by when appropriate is that actually SU3 QCD with quarks in the fundamental representation are strictly speaking not a confining theory. And that may sound weird, but it actually is the case. And I tell you what the criteria are in a moment. So when appropriate, like going to a different gauge theory, you can show the confinement actually does happen. And there has been also this problem that the QCD Lagrangian has U3 cross U3 flavor symmetry, and it's broken to U3. So there's also U1 Goldstone boson as well. But we know such a state is heavy from the experiments, and that is what is usually called the U1 problem. And the candidate U1 Goldstone boson is what we regard as the eta prime in the pseudoscalar mesons. And so you can, in this case, you can calculate what the eta prime mass squared is and show that it's indeed non-zero and heavy. And you can derive chiral Lagrangian now that you have broken through chiral symmetry. And chiral Lagrangian also comes with something called a hidden local symmetry. That's what people phenomenologically came up with in the construction of a low energy theory. And also is accompanied by Vesumino-Witten term, which can capture all the anomalies present in the global symmetries. So that can also be derived. And you can also study various limits, like large NC limit, For example, you can show that F pi squared is indeed order NC as it should be. And you can also compute these non-perturbative condensates, Q bar Q condensate, glue condensate, and you cannot compute these things in perturbation theory, but in this technique, you can actually compute them. There is a rather strange formula we came up with on topological sustainability that how the vacuum energy depends on the theta parameter of QCD, which turns out to be related to the mass of the eta prime I talked about earlier. And that's something you can explicitly calculate as well. And this is something I did not expect initially. So the pions and eta are all pseudo-scalar mesons, parity odd states. But it turns out that in this theory, they are accompanied with parity even states as well. And it turns out that there are light spectrum or parity even states in QCD, which we can also compute in this framework. And they at least qualitatively very much agree with what is shown in data. And finally, once you have this framework available to you, not only that you can apply to QCD, which of course you like to understand, but there are many other theories you would like to understand, especially chiral gauge theories. And these theories had never been simulated even on lattice, which is very difficult to do. But in this framework, you can again solve exactly the non-perturbative behavior of these theories and make a prediction on what kind of symmetry breaking you would expect in these theories. And especially those points I put in color are not even possible on lattice, but you can do it rather on piece of paper using this technique, and that's what I would like to tell you today. So I stop here for the moment. Any questions about where I'm going? Is it good?
So there is no real way of putting chiral gauge theories. There is no this domain wall.
Well, people have talked about it, but it have not been done.
Not been done.
Yeah, it's still very difficult. All right, so just a little review of QCD. So we like to understand the nature of strong interaction. And so back in grad school, I remember that I was taught about quarks. So here's a proton. And if you look inside, you're supposed to see 3 quarks. They are colorful, beautiful, but you never get to see them. That's what you get told, right, in classroom, because quarks are confined. So I felt like this was a scam of some sort. And when I looked into my mailbox, I still could find this, typical Nigerian scam emails. So I felt like this, I've been fooled. I'm supposed to buy into the existence of these quarks, even though I can never see them. So that left me uncomfortable. And of course, we get told right away, well, but that's okay, don't worry about it, because there's something called confinement that's happening here. But how exactly is the confinement happening is still a question mark. And we do learn the beta function in QCD is negative, and that's beautifully shown in the experimental data these days. So the theory becomes weakly coupled at high energies, theory becomes strongly coupled at low energies, but becoming strongly coupled at low energies doesn't necessarily mean that theory leads to a confinement, because we are aware of other theories that reach the infrared fixed point, which is strongly coupled. So it's definitely not a theoretical proof of any sort. So it's only suggestive. Doesn't prove confinement. And another puzzle, which is really at the heart of physics happening here, is that proton and pion are made of the same quarks, up and down quarks, everybody knows that. But pion is much, much lighter than proton. And this lightness of pion is actually very important for us to exist. So if you look at the spectrum of hadrons at the low energies, here's the pion, and here is the proton, and this is the rho meson. So there's definitely a big gap between pion and the rest of the strongly ionic particles, even though they're made of the same things and subject to the same confinement. And of course, the Nambu told us to understand this pion is supposed to be the Nambu-Goldstone boson. But before getting there, so if pion is not so light, what would happen is that if you think about the strong force from proton acting on neighboring proton and neutron inside the nucleus. If pion is heavier, it doesn't go very far, even to the next proton inside the nucleus, so they do not get bound, unlike despite what Yukawa told us about this interaction. Pion needs to be light enough so that the pion exchange would lead to the next nucleon inside the nucleus, so they can be actually bound together to form nuclei. So if the pion were heavier, this entire periodic table we have to rely on for existence would totally disappear, and universe is made only of hydrogen because there will be no nuclei. So the lightness of pion is really, really important for us to exist. So we start to learn new things beyond this initial stage of introduction to QCD. And there are some qualitative pictures that might make us feel better about the picture in QCD. So in the case of confinement, that goes back to my late colleague Stanley Mandelstam, who told us that you may be able to understand confinement based on other physics we are familiar with, namely the Meissner effect in type 2 superconductor. So what's going on in a superconductor is that when you have a magnetic field getting into a piece of superconductor, it gets squeezed into a tube of magnetic flux, called abrikosov flux. And because it's actually a form of tube with a constant magnetic field inside, the total energy of the tube will be proportional to the overall length of the tube. So if you actually then do a switching from electric degree of freedom to magnetic degree of freedom, what happens in a superconductor is a condensation of Cooper pair electrons. So what you're looking at is a system where electric charge is condensed. Instead, if you assume that you have a system where magnetic charge is condensed, that is the monopole condensation, then instead of having a magnetic flux squeezed to a tube, electric flux will be squeezed to a tube. So if you actually place an electric charge like quark color charge plus and quark color charge minus into a system where you have this monopole condensation, then electric field between the quark plus and quark minus will be squeezed into a flux tube, and therefore energy is proportional to the distance between quark and antiquark. And if we have a potential energy that's linear in the distance, that is the basic definition of the confinement. So linear potential means the derivative of the potential with the force is constant, no matter how far away you go, so you can never liberate quarks and antiquarks, and that is indeed the idea of confinement. And what Nambu told us is that the lightness of the pion is a consequence of this idea of spontaneous chiral symmetry breaking. It's really amazing that even without knowing about quarks or QC Lagrangian, he could see that there is the secret SUNF cross SUNF global symmetry in strong interaction physics, which is supposed to be broken to SUNF by a Q-bar-Q condensate. In his paper, it was a nucleon-nucleon condensate, but it's the same thing as far as the flavor symmetry goes. And because of this spontaneous symmetry breaking, you induce massless Goldstone bosons. But this chiral symmetry is slightly broken by the mass of the pion, and that's why pion is finite mass, but still light, and therefore can mediate the strong binding force into the nuclei to the neighboring nucleons so that nuclei can bond together. So that is the picture we get told in textbooks and classrooms. But what I'm emphasizing here is that in the case of this dual Meissner effect, you are assuming monopole condensation. You are not deriving it from QCD anyway. And also for the chiral symmetry breaking, we are assuming this pattern of symmetry breaking. Again, we are not deriving from the fundamental theory in any way. So that's where I was still being frustrated that somehow I don't understand it. And of course, there had been the great progress done in the 90s, where Seiberg and Witten start to produce the exact solutions to spherical cow supersymmetric gauge theories, which is still not quite the same as QCD, but at least in this case, you can solve the theory exactly. So specifically what they have done is to take SU2 gauge theory, they make it supersymmetric doubly. You have two sets of supersymmetries in the system, and realized that there is an infinite number of degenerate ground states to the system, where generically SU2 gauge could be broken to U1. So this is actually Coulomb phase of the gauge theory. And on this space of all possible ground states called homogenize space, they could identify the existence of magnetic monopoles. because whenever you break SU to U1, there's a topologic of monopole generically on this space of ground states. And in particular, there are special points on this space of ground states where this magnetic monopole non-perturbatively becomes massless. And that's actually somewhat not too surprising, because once you actually go to a point where gauge coupling becomes larger and larger, the mass of the monopole is expectation value over the gauge coupling constant. So the monopole becomes lighter and lighter. But they came up with a very vigorous argument why they actually do become exactly massless at specific points. And then by breaking this n equal 2 supersymmetry down to n equal 1 supersymmetry, they could demonstrate that this massless monopole ends up acquiring an expectation value, realizing the condensation of magnetic monopoles, and therefore that's a demonstration of a confinement. So far, that's really great. But when you actually want to think about chiral symmetry breaking though, so this world with two sets of supersymmetries have two high degrees of symmetries, it turns out that there is no chiral symmetry to begin with. So you cannot really discuss the physics of chiral symmetry breaking using this setup. So Naty-Seiberg then went on and studied a system with fewer supersymmetries, which are called n equal 1 supersymmetry. And he could still solve the theories exactly, which is again wonderful. But it turns out the solutions end up not looking like the real world at all. And so how different they actually look is I'm trying to show in the slide here. So let's say you're talking about supersymmetric gauge theory, which is on this line, which I labeled m equals 0. And m ends up being how much you break supersymmetry at the end of the day. So m going to infinity is the non-supersymmetric world we live in. But now I'm looking at the Seiberg solution exactly when supersymmetry is still there. And thinking about SU and C gauge theory, it turns out that when the number of flavors is here, between 1 and NC minus 1, the theory doesn't have any ground state. It has a behavior called runaway behavior, that supersymmetric gauge theory has scalar partner of the quarks, squarks. Squarks end up going all the way to infinity, and there's no ground state. It asymptotically goes to zero energy, but there's no point where you find the ground state. So that doesn't look like QCD at all. Of course, we believe QCD has a ground state, but this theory doesn't. If you go to higher number of flavors, you might find a theory which actually confines that the quarks appear in meson and baryon bound states. So that's great. But there are ground states that don't show chiral symmetry breaking. Again, that's not quite what we would like to see in QCD. And that's also true, even if you go to one step higher. If you have more flavors, something really bizarre happens. So quarks start to getting confined into baryons, but the baryons break up into smaller pieces, which are transformed under a different gauge group from the original SUN gauge group, which is called the magnetic gauge group. And that magnetic theory is infrared free. So in the low energy limit, you end up finding the set of quarks and gauge groups, which is weakly interacting, but different quarks from what you started with, and different gauge bosons from what you started with. Again, that's not something we expect in QCD either. If you go to higher number of flavors, you have an infinite fixed point, which we may expect in non-SUSY QCD too, but probably for different numbers of flavors. And if you go to a very large number of flavors, of course, beta function sign changes to positive, then you have an infrared free theory. So point here is that supersymmetric limit had been solved by Naty-Seiberg, but it doesn't look like the theories we want to study. What do we know in non-supersymmetric limit is very limited. So if you go to very, very high number of flavors, we know it becomes infrared free. And just below this limit, do we believe that theory does flow to infrared fixed point, but at a higher number of flavors than we see in a supersymmetric case. Now, for the lower number of flavors, we basically know that theory should break chiral symmetry because of the data. And of course, lattice simulations strongly support that idea. And in between, we don't really know what's going on there. So what I'm trying to show you today is that if you are close to supersymmetric limit, but do break supersymmetry explicitly by introducing a parameter, you can still solve the theory exactly, non-perturbatively, and all of a sudden, all of these different number of flavors seem to lead to chiral symmetry breaking, which is the behavior we want to see in non-SUSY QCD. There are some tricky issues I have to mention later, but this solution near the SUSY limit may or may not be fully connected to non-SUSY limit, whether depending on when you cross this strong scale, whether the phases are continuously connected or there's a phase transition at this moment. And I do not have a proof that there is no phase transition and therefore they are continuously connected, but I can show you many circumstantial evidences that they indeed are. And that's the way I try to claim that exact solutions you can obtain here are telling us about how non-perturbative gauge theory should behave without supersymmetry. So that is the main claim. And so what is happening in the non-SUSY gauge theory is most likely based on this picture that is chiral symmetry breaking all the way up to 3NC. And then it may be switched to infrared fixed point for higher number of flavors. And that's the picture I have. And here, definitely, they seem to be continuously connected. Here, there may be a phase transition, but there's a local minimum that seems to be continuously connected. So there's still something you can learn by studying the local minima. So that is what I said at the very beginning. So to understand the real cow that is sitting on this non-SUSY limit, you can actually make it supersymmetric all the way to this end once. And by breaking it a little bit, you can start picking up the features of non-SUSY gauge theory at the end of the day. So that is basically the claim I'd like to make. And we actually have seen this kind of situation in different systems in physics. That is what is called the BCS-BEC crossover. So in atomic physics, you can have a cold gas of atom, and each atom is a fermion in this case. So there's no Bose-Einstein condensate of those atoms because it's fermion. And if you have the zero coupling among them, it's just a fermi-degenerate gas, like what you see in a piece of metal. But when you actually introduce a small attractive force among the fermions, then they would undergo the BCS state, which you use to describe the superconductivity or superfluid of helium-3. And so in the BCS state, the U1 symmetry, which corresponds to the conservation of the number of particles, is spontaneously broken because the pair of fermions has an expectation value, the Cooper pairs. So U1 is broken. And when you jack up this attractive force between fermions, at some point, you need to switch to a non-perturbative description, namely that two fermions end up forming a bound state and become a boson. And that boson can become a Bose-Einstein condensate, so that again, U1 symmetry of the number conservation is broken. And it is known that these two limits are continuously connected without a phase transition. And that is the behavior called BCS. That's the small attractive force limit. And BEC, that's a strong non-perturbative attractive force limit, are continuously connected, namely crossover. So what I believe what's going on here is that also in the non-perturbative gauge theory, small SUSY breaking is where you can analyze the system exactly, and you can show certain symmetries are broken. Strong coupling limit corresponds to large supersymmetry breaking. And as long as they are continuously connected, what you can work out here would tell you something about what's going on over there. So we do have systems like that elsewhere in physics, and I believe the same thing is happening for non-perturbative gauge theories. So that's the picture. And there are many references here I don't go through, but now I see a hand up, so please go
On
ahead.
the previous slide, is there necessarily a phase transition to reproduce the conformal window though? That's sufficiently large enough?
Yeah, so that's a good question. So what you can, could show near the supersymmetry limit is that there are the ground states which break flavor symmetry in a different way from what you would expect from chiral symmetry breaking. And so from here to there, there seems to be a phase transition between them. But nonetheless, once you actually break supersymmetry explicitly, to here, the symmetry does break, so theory is not conformal in the infrared limit, and that's what we found. On the other hand, when the flavor is not bigger than 3nc, the SUSY side of the gauge theory, it becomes free, so we don't get any non-perturbative dynamics there. So by introducing SUSY breaking and gradually going to the other side, we don't have tools to analyze what's going on in a non-SUSY limit necessarily, so we are not getting any extra information about that. So that's the limitation of our method.
So in that case, above 3nc, you would say there has to be a phase transition to reproduce the non-supersymmetric.
Yeah, that's right, right. Okay, so before getting into, yes.
Sorry, in that last picture, when you're transitioning, when you're turning on a little bit of, you're breaking SUSY a little bit, you
Right.
already get this transition chiral symmetry breaking, even from an infinitesimal amount of SUSY breaking, or you need to break like a.
So we cannot solve the theory when supersymmetry breaking becomes as large as the dynamical scale. So the exact solutions I can show is what I can obtain only for small supersymmetry breaking. So we have to put a faith in this possibility that what we learn here does connect smoothly to what can happen here. In the same way as the BCS-BEC crossover happens, then we are learning something about non-perturbative QCD by studying near supersymmetry QCD. So that's all I can say in a rigorous way. But there are many things you can do with small supersymmetry breaking, which looks very much like what we believe should happen in non-SUSY QCD. And given that there are so many evidences, I now believe in that picture. But if I can convince you, it's something you can tell me afterwards. Okay, that's the best I can say. Yeah, so the first thing is I have to give you a little review of global supersymmetry. So supersymmetry algebra is an extension of the Poincare symmetry of the Minkowski spacetime. And we know these the commutation relations among the translation and the Lorentz generators. In addition, we have these fermionic charges called supercharges Q alpha, which is actually a spinor under the Lorentz transformation as indicated by this commutation relation. The Lorentz transformation acting on supercharges is actually a spinor representation of the Lorentz group. And also that the supercharges Q and their Hermitian conjugates have the anti-commutator that will give you the four momenta in space-time. And you can develop the representation theory for this right away if you specialize to the case of the massless particles. And then the supercharges would basically give you this kind of fermionic harmonic oscillator. And so we know right away what the Hilbert space looks like, namely that this P-Dagger operator increases the helicity by 1/2 unit. So you could have a multiplet where you have a pair of fermion with helicity -1/2 and scalar boson with helicity 0. So this kind of multiplet is called chiral multiplet. So we believe this may be what's happening with, for example, the left-handed lepton in the standard model paired with the scalar leptons and also for squarks. And Hermitian conjugate of that is the pair of the scalar particle and helicity +1/2 right-handed fermion. You can also have a multiplet between spin helicity 1/2 and helicity 1. And helicity 1 has to be a gauge boson in Riemann-Roch gauge theory. So this kind of multiplet is called vector multiplet, namely that you have a gauge boson, like a photon, paired with a fermion with helicity 1/2, that's a photino. So gauge boson and gaugino, so that pair is called the vector multiplet, and this is just the complex conjugate of that. So this is in general the structure of multiplets in global supersymmetry. And once you know what kind of particles are there, you would like to write down the field theory with it. And to write field theory, you need to use this realization of the Lorentz groups, namely that the momentum operator is just a derivative, and so on and so forth. And in order to write this supersymmetry transformation also as a derivative operator, we do need this strange idea of the fermionic spacetime coordinate, that's the Grassmann odd coordinate theta. So x, the usual spacetime coordinate, the four of them, come in a pair with the fermionic coordinates, and generic fields called superfields function of not only x, but also of theta. So you're extending the notion of space-time. And once you do that, you can write supersymmetry as a derivative operator like any other symmetry generators of space-time symmetry. And furthermore, we would like to write down a Lagrangian with derivatives in them to write down, for example, the kinetic term of fields. And you need to make sure that derivatives are consistent with the supersymmetry transformation. So we need some special derivatives we call covariant derivatives that anti-commute with the supersymmetry generators so that we can use them to write down Lagrangian. In particular, we can place also a constraint on some of these super fields, which is a function of x theta and theta bar. And if you use this constraint, you can write down a solution to the constraint in terms of a complex scalar field, left-handed Y fermion, and some auxiliary component. So having complex scalar field and Y fermion is exactly the multiple structure I talked about on the previous slide. So this superfield is achieving the goal of writing down the theory with the multiplets I talked about based on supersymmetry. And this is just a little detail I'm going to skip. And I can also study how the gauge multiplets or vector multiplets can be written as a superfield. So general function of x theta and theta bar can be expanded this way. And remember that theta is a fermionic Grassmann odd variable and it's spinor, so we have two of them. But if you multiply theta 3 times, you don't have already exhausted all the components, so that's identically vanishes. So any function of theta and theta bar can be expanded in power series in theta and theta bar, which would end when you use 2 thetas and 2 theta bars. There's nothing beyond that. And you can show that even though this is a general, rather complicated form, there is actually gauge redundancies you can use to eliminate most of these components. Then the rest looks like the standard gauge field. And here's the fermion field, which corresponds to gaugino field. And again, some auxiliary component that doesn't have dynamics. So this is the way you can realize the vector multiplet I talked about 2 slides ago. So these are the ingredients you can use to write down your Lagrangian. And to really implement the gauge invariance, this V has to be summed up with all the gauge generators. And they actually transform in this particular way. And this lambda is a gauge parameter, which by itself is a karaoke superfield, so that you can eliminate all of these components I mentioned earlier and end up with only the physical components you need for the purpose. So remaining degree of freedom is really just a gauge boson of spin 1, gaugino of spin 1/2, and something not dynamical you can eliminate. And there's a specific way of writing down the field strength where F mu nu indeed appears in the expression, which is manifestly gauge covariant. And 2 more slides on technical stuff. And when you write down the Lagrangian consists of 2 pieces. One of them is called scalar potential, which basically gives you all the kinetic terms. And another piece called the superpotential, which gives you interactions, roughly speaking. And once you have this superpotential W, which is the function of the chiral superfield, which is expanded up to order theta and order theta squared, you can integrate over theta to get the Lagrangian, which looks like this. And here you can see, for example, Yukawa coupling between scalar and fermion. And here's the auxiliary component you can eliminate. And after eliminating it, so F turns out to be this del W d phi. And so this actually ends up being the potential for the scalar particles in supersymmetric theories. And one interesting fact about supersymmetry is that when you actually think about how different things renormalize, when you go from some high scale to low scale, this superpotential does not get renormalized, something called non-renormalization there, stays put. The only renormalization you get is the wave function renormalization for the chiral superfields, and also one loop running of gauge coupling constant, and that's it, nothing else. But it turns out that even though the gauge coupling seems to run only at the one loop level, in order to really read off the beta function, you have to change the normalization of gauge field absorbing the gauge coupling constant to make the kinetic term canonically normalized. That's what we do normally in QFT textbook. And when you do that, the scaling of fields, actually path integral measure is anomalous under that. So it turns out that in the paper we've written when Neil was still a grad student in Berkeley, even though the running seems to be only one loop, when you change the normalization of the gauge field to make it canonical, and also change the normalization of the matter fields to make it canonical, that would actually induce some anomalous Jacobian. So it turns out that you get contribution, which depends on the wave function normalization factor, giving a contribution to the running of the gauge coupling constant. And when you further scale it, you get additional piece, which is the log of the gauge coupling constant. So out of this, you can get the exact beta function to arbitrary order in perturbation theory. So supersymmetry is much more rigidly built compared to the usual quantum field theories that you know a lot more about these properties and the renormalization and so on and so forth. So that's the end of the technical stuff. Now that you have seen how to write a supersymmetric theory, now I need to tell you how we are breaking supersymmetry based on this scheme called anomaly-mediated supersymmetry breaking. So our needs is that we want to connect these supersymmetric theories, spherical cow, to a real cow by breaking supersymmetry. But you have to make sure that at least we're moving in the right direction. And in order to do so, we have these gauginos that are part of the gauge bosons, and we don't need them. We haven't seen gluino yet, so we need to make it massive. We also have the superpart of the quarks, namely squarks. We haven't discovered them either, so we need to make them heavy too. So at least we need to make both gauginos and scalar particles heavy by breaking supersymmetry. And ideally, we can do it on one shot with only one parameter in count. At the same time, this is a much more difficult requirement. We are dealing with, ultimately, the confining theory, so that you will be talking about mesons and baryons instead of quarks and gluons. And when you break supersymmetry in some arbitrary fashion, you would not know how these bound states would acquire the impact of supersymmetry breaking. And that is actually a much more difficult requirement. And so we need to know, for example, what kind of sign of the masses the scalar fields would acquire. Otherwise, you don't know if the symmetry is broken or not. So you need to know this connection between the supersymmetry breaking in a UV theory to how they would appear in the IR. It turns out that there are two known ways of doing so. One of them is anomaly mediation. Another one is called U1RD term. But U1RD term doesn't satisfy the first requirement to make the gauginos heavy. So if you'd like to simplify the problem with only one scheme to satisfy both requirements, you have to use anomaly mediation, which turns out to be very useful.
When you say URR is part of the super conformal symmetry, or just
That's right.
engineer you, okay,
Right.
that's why it's restricted.
Right. And so another problem with URD term is that you know how that works in the IR limit, but not necessarily in between. So that's another advantage of anomaly mediation. And this idea of trying to see how symmetry breaking would impact IR physics is, of course, known exercise, which we do in chiral Lagrangian itself. You are breaking chiral symmetry by quark mass, and you try to read off how quark mass would impact the physics of pions. So we are relying on some external symmetries outside the strong dynamics. And as long as those external symmetries would determine how symmetry breaking appears in IR theory, that's something what we would like to know. So I already mentioned quark mass in chiral Lagrangian is an example of this. So looking at the QC Lagrangian, and up to this point, you have SUNF cross SUNF chiral symmetry. Once you introduce the mass of the quarks, it's no longer invariant under SUNF cross SUNF, but pretending that M is not a parameter, but something that transforms under this SUNF and SNF symmetry called spurion, you know exactly how that spurion would appear in the low energy theory. The low energy theory is assumed to depend on this chiral field U, which transforms under SUNF cross SNF. But because we are pretending M to also transform under SUNF cross SNF, you can write an invariant under it. So that's how you determine how quark mass would enter the chiral Lagrangian. Then you find a surprising conclusion that the pion mass grows as a square root of quark mass. Naively, if you make the constituent of the pion massive, you might think that whole thing would acquire mass linearly with the mass of the constituent, but it doesn't. It goes like a square root. So knowing how symmetry breaking in a UV would appear in IR is a non-trivial problem in general. And that's exactly what we need to do, also replicate when you break supersymmetry and see how a controlled supersymmetry breaking would appear in IR physics. And I think I'm going to skip this slide. And in order to achieve this goal, the way we can do this supersymmetry breaking is to decouple whatever physics that may break supersymmetry to the theory we like to study, whose connection is only through gravity. And if you do that, without any direct connection between them, that the way supersymmetry breaking would appear in the gauge theory you like to study is completely controlled by supersymmetric version of general coordinate invariance. So namely, this supersymmetric version of general coordinate invariance called supergravity is an external symmetry that tells you how this supersymmetry breaking in a UV should appear in the IR theory. So that is the reason why this actually turns out to help us. And so this idea of anomaly mediation is something I propose mostly for phenomenological purposes with the Riccardo Rattazzi, Marcus Rudi, and Giudice quite a while ago. And this is the time I was saved by time differences in the world. The time difference is something I always hate because when you travel, I get jet lag. Even 2 hours jet lag from California is haunting me right now. So that's something I normally hate. But what happened to us is that we were together at CERN in summer '98. We worked together on this idea. We already had a half-finished draft. But after everybody went home, we got busy with teaching and all that stuff. So the draft was kind of left out over there and sitting on a computer. But one day, when I was checking the archive in the evening in California time, we found a paper written by Lisa Randall and Raman Sundram, which had exactly the same idea in it. And I freaked out. So I emailed my friends and asked them, what should I do? And then that was the evening in California. So my friends, Gian Giudice and Riccardo Rattazzi, son, were just coming into the office. And then they told me, okay, it's late for you. You go to bed. We have a half-finished draft. We try to finish that up. So you go to sleep. So they started to work on the draft. And when they go to dinner, they handed the paper over to Marcus Rudi, who was at the East Coast that time, at Maryland. He kept working on the draft. And in the end, the draft came back to me. I finished it up, submitted an archive. So the papers appeared only with 1 day difference at the end of the day. Otherwise, I couldn't have received 1630 citations for this paper. So this was really the time when time difference saved us. So otherwise, I would hate time differences. But at the end of the day, what you need to know is only this. So when you use this scheme called anomaly mediated supersymmetry breaking, there are 2 ways the SUSY breaking might appear in IR theory. One is at the tree level, and for any given superpotential you add this term. So that's one piece. Another piece that appears at the loop levels is that you get a gaugino mass proportional to beta function, scalar mass squared proportional to enormous dimension and its derivative, and another thing called trilinear coupling proportional to enormous dimension. And this is where it actually makes sense, because everything is going through anomaly of conformal invariance in this theory. If you take the gauge theory, it's classically conformal invariant because gauge coupling gets dimensionless. But because gauge coupling constant ends up running, it does break conformal invariance. That is what is called the trace anomaly. And how much conformal invariance is broken is therefore described by the size of the beta function. So no wonder gauge inner mass is produced proportional to the beta function. And also for the matter fields, how much conformal invariance is broken is that you get these anomalous dimension factors. So you get SUSY breaking proportional to anomalous dimension factors. So that's the projection in this scheme. And even more importantly, these formula tell you that you only need to know physics at the energy scale of your interest to understand how supersymmetry breaking appears. So when you compute the beta function in QCD, you don't talk about extra gauge bosons at the gut scale. You have already decoupled them. And this formula tells you that you don't need to know what's going on at the gut scale. You only need to know the particles that exist at the energy scale of your interest. The same here, same here. And this is a property we call UV insensitive. So if you have defined the SUSY breaking at the UV theory, you don't need to follow through everything in between. You just go to the IR limit, and just knowing the IR limit, you know how supersymmetry breaking effect would appear in the IR theory, and that's how you can actually end up solving the non-perturbative consequence of gauge theories.
Hitoshi, gamma dot I in principle should be negative, right? So then
Which is negative, you said?
the mi square should be positive, right?
Yeah, it could be negative too, yeah.
But wasn't there a problem in the Slepton sector?
So that was a phenomenological problem, that if you want to use this scheme for LHC phenomenology, the Slepton couples to use U1 hypercharged gauge boson, which is asymptotically non-free with a positive beta function. So you would predict the Slepton mass is negative. But here, we're not doing phenomenology with it. We are trying to use this as a way of solving strongly coupled gauge theory. So by definition, you are interested in asymptotically free gauge theories where beta function is negative. So you don't have a problem of negative mass squared for squawks in a UV theory. You may still generate negative mass squared in IR as a consequence, but that's okay. That's a signal of certain symmetry break. But in the UV theory, it's well-defined and stable and no problem with that. Thanks for the question. Okay, so that's the idea. So now we end up putting the Seiberg solution to non-perturbative gauge theory in supersymmetric limit with the scheme of supersymmetry breaking I just talked about and see what we get. Any questions at this point? Okay, that was a long introduction, but now finally coming to the crux of the results. So when the number of flavors less than number of colors, the Seiberg's result is what I told you already, is there's no ground state. And it's described by the scalar field going to infinity because of the superpotential, which is inversely proportional to these meson fields. So if you write down the potential out of this superpotential, the potential actually looks like this red one. And the squawk would keep turning on all the way to infinity and eventually asymptote to zero, but there's no stable ground state in the system. But I told you already how supersymmetry breaking effect would appear at tree level for a given superpotential. And that's the second term over here. And once you include this, the potential becomes the blue one. And now you see a stable ground state with a finite value of this meson field. So first of all, you do find a ground state. And second, because this behavior, the ground state at the minimum of this blue potential has this meson field non-zero in such a way that turning off supersymmetry breaking, sending M to zero, would bring the meson field to infinity, so you can go back to Seiberg's result that way. So there's nothing inconsistent with it. Third, because the meson field has an expectation value here, and you can show that it's really proportional to the identity matrix, then that is a demonstration that SUNF plus SUNM flavor symmetry is broken down to diagonal subgroup. That's the chiral symmetry breaking. So what Nambu conjectured, what the QCD should be doing is something you can see on one slide that QCD does do that, at least near the SUSY limit. And once you know that this SUSY breaking happens, then you can write down the chiral Lagrangian. I will show that on the next slide. But when you do so, the meson as a partner, mesino, I might call, the fermions, which you also need to integrate out. And when you integrate mesino loop, you can show that that also induces the Vesumino-Witten term you are supposed to have in a chiral Lagrangian, so that you can explain how pi naught decays to gamma gamma. And that also automatically comes out. I'm not showing this here, but believe me, it does. You can also ask the question, what happens when number of flavor is 1? And U1 flavor symmetry is anomalous, and therefore corresponding Goldstone boson becomes massive. That's the way we want to understand the U1 problem I talked about at the very beginning. But now that you have this potential, using this potential, I can compute the mass of the would-be U1 of Goldstone boson and show that it is indeed massive. Eta prime is massive. And you can do so also in the presence of other flavors too. So you can see how U1 symmetry being anomalous end up really providing the mass for this U1 gauge Goldstone boson. And that's an explanation to the U1 problem.
Can I ask you,
Oh, go ahead.
can you clarify what if anything you're assuming about the Kähler potential?
So in this case, the minimum end up being far away from dynamical scale in the limit of small supersymmetry breaking. Therefore, Kähler potential can be well approximated with the canonical UV Kähler potential for quark fields, where the theory is weakly coupled. That's the question?
Sort of maybe,
I'll speak on phone.
Okay,
I bought a new phone apparently.
can you remind me why the Kähler potential becomes canonical in the large field limit?
So when supersymmetry breaking is small, that's what we're assuming, then this field value is large compared to the
Sure,
dynamical
that
scale.
part I get, but
Yeah.
why does the Kähler potential become canonical?
And so when the field value is large, what you're talking about is a D-flat direction made of quark and anti-quark. And they are at UV degrees of freedom, where the UV Lagrangian is a canonical Kähler potential for them. Because we're talking about renormalizable gauge theory.
Okay.
You happy?
Yeah, kind of.
Okay.
So I feel like the true n equals 0 limit is m goes to infinity.
So
You get-
all I can, I said this before, all I can do is solve theory when m is small.
Yeah, okay.
And then you hope that that solution you get are continuously connected with a large m limit. And I show you circumstantial evidence, but I cannot show the proof.
Okay.
Okay, so that's what you see already at this stage. And now that the symmetry is broken, I can parameterize the quark field using this matrix C. And you know how they transform. And this transformation property is exactly what Callan Coleman Vesuvino told us how the chiral fields should transform. And out of them, I can define this chiral field U, which you use in chiral Lagrangian. And all you need to do is to rewrite this canonical kinetic term for quark fields using this C field. And that actually turns into the usual form of the chiral Lagrangian. So that's a derivation of the chiral Lagrangian. And out of this derivation, you can read off what the pion decay constant is, which looks like this. And at this moment, there was a paper by Steve Martin and James Wells who looked at this kind of formula with a different method and said, well, this looks like order 1 in large NC limit, but f by square is supposed to be order NC. That's an inconsistency. Therefore, they are not continuously connected. There must be a phase transition when SUSY breaking is of the order of the dynamical scale. That conclusion is wrong. Because as I told you already, when you go to canonical normalization of fields, you have to include these anomalous Jacobians in definition of the gauge coupling constant. And if you do that job a little bit more carefully, the dynamical scale that appears here ends up picking up the factor of NC by rewriting it in terms of tooth coupling. So F pi squared is indeed order NC, and that's the expected behavior. And taking large NC limit is not what you can do on lattice, because you can't deal with the infinite size gauge group, but here you can do that again on a piece of paper, and F pi squared is indeed order NC. So there's no sign of the need for phase transition. And for the U1 problem, I mentioned this U1 Goldstone boson already, and U1 symmetry is anomalous. That's why people say that there's no problem with the lack of U1 Goldstone boson. But in this scheme, you can really compute the mass of the eta prime squared. And Witten told us that eta prime mass squared must be order 1 over NC. Once again, by taking the limit where NF over NC, x goes to 0, this is order x, and therefore 1 over NC. Again, that is the behavior you expect to see in QCD. But in addition, we have 4 x dependencies in this formula. And this x dependence is nominally higher order in 1 over NC. And so you are seeing the order corrections coming from the large NC limit at the same time in a simple expression. And in addition to arguing that this must be order 1 over NC, Witten also wrote this formula again in the large NC limit, which is a very strange formula. So you compute this topological susceptibility when in a theory with pure Yang-Mills, no quarks in them. And then he argued that that topological susceptibility in theory with no quarks is related to mass of the eta prime with quarks. And of course, when you have massless quarks in the theory, theta parameter is unphysical. You can rotate it away. So there's no topological susceptibility in the theory with quarks in them. So no wonder why he had to do it. But they are different theories. You're comparing no quark theory with quark theory. And in the large NC limit, they're supposed to become equal. And that's the Witten statement. And here we can show that. So F pi, we computed already. M eta prime squared, we computed here. Taking the product, sending x to 0, this is the limit. We can also compute this topological susceptibility in theory without quarks. That actually turns into this one. And by multiplying 2 and f, they are exactly the same. But you can also see the violation from large NC limit, that the reason why they said they power x here is because there are 2 different theories with 2 different beta functions. Gauge coupling constants run in different ways, so the dynamical scales are different between these 2 theories. So that's captured in power x here. In addition, the prefactor here is the correct contribution of the glue state mixing to QQ bar state. This mixing is 1 over NC, but comes with NF because of the core group in there. And this kind of mixing effect goes away in the large NC limit, but for finite NF, you can capture all of these mixing effects in this simple compact formula. So you're getting a lot more information this way. So you can really see expected behavior in large NC, but in addition, you capture all the information for finite NF and finite NC at the same time in the way you would expect in QCD. And I already argued that not only that you can compute this condensate of squawk fields, you can also compute the condensate of quark fields too, which is non-perturbative, but again, you can work it out. And you can also compute the condensate of gauginos, but also condensate of the gauge bosons, glue condensate, all in a function of M and NF and NF. And you can show that small NF MCM behavior are some kind of power laws. And we cannot do really anything when the SUSY breaking is comparable to dynamical scale. But if you go the opposite limit for non-supersymmetric QCD, at least you know how you would expect these condensates to behave as a function of SUSY breaking. And that's the line on this side of the gray band. And at least you can see that they seem to connect continuously. This is not a proof, but it's a circumstantial evidence that there is no phase transition between them. The theory is continuously connected from near-SUSY limit to non-SUSY limit. And you can also compute a kind of question you can never do in the lattice gauge theory or even the large NC discussion. So I told you already f pi squared is indeed order NC when NF is up to NC. But now that I can solve the theory exactly, I can also ask the question how f pi depends on NC and NF when NF is as large as NC, and this is the behavior. And in the large NC limit, you only don't talk about these planar diagrams where core group is filled with a bunch of gluons in between. But when NF is also large, you have to consider these punctured planes too. And this expression captures all of these contributions as well. So the fact that the behavior starts to deviate from large NC limit when NF is large is not surprising. And you can see that that's indeed what happens. And now that we have the theory, you can solve exactly. You can work out the mass spectrum. And in the massless quark limit, of course, you do get this octet of the number Goldstone bosons, like what you expect in chiral-Lagrangian. But these pseudoscalars are paired with the scalars with positive parity in this chiral multiplet, whose masses you can compute too. And this is the data. Of course, you need to put in the finite mass of the quarks into the calculations. So what used to be massless Goldstone bosons now acquire mass proportional to the square root of a quark mass I mentioned earlier for pions, kaons, and eta prime up there. It turns out that you also have the low-lying 0+ positive parity spectra, which forms the SU3 multiplets. And these states used to be very controversial for almost half a century, whether they actually exist or not, like a sigma particle. And I grew up in a generation where sigma particle doesn't exist. Linear sigma model is just a toy model. You have to go to non-linear sigma model because you integrate sigma out, and that's nothing but the chiral-Lagrangian. But these states are now experimentally established, so they exist. And then also you can see is that spectrum of the 0+ states are upside down. Isotriplet here, isotriplet there. Strange states here, strange states there. Singlet state here, singlet state the lightest. So it's an upside down spectrum. It turns out that these states are now experimentally established because you can produce them top down in E + E- experiment from B decay and D decay. That's why you can see very clear peaks of these resonances. Yes.
On the previous slide, I'm confused about the logic of this slide. I thought that if we take the SUSY theory and do a small mass deformation of it, we would have tons of massive states that have probably nothing to do with the non-supersymmetric theory, because we haven't yet taken the mass to infinity. So how can we compare the massive spectrum?
That's an excellent question. And indeed, I was not expecting to learn anything out of this exercise. But when we actually went ahead and computed the spectrum, it turns out that 0+ spectrum you can compute, which is lighter than these singlet states, are still very much consistent with the data. And that was a surprise to us. So this method is doing better than I expected. That's what I'm trying to say here. So
So
use
those states that you found, do they, if you dial up the SUSY breaking mass, do they move? Or do
yeah,
those
they
states-
move. They are proportional to SUSY breaking. Yeah. So it becomes heavier and heavier.
So what
But
do you
in some sense, SUSY breaking scale is giving you the cutoff of the confinement scale in the physical intuition. And these states seem to stay even in the non-SUSY
So you
limit.
want to set roughly m squared to be lambda squared.
In the end, yeah. So that seems to be the right interpretation of this result. And another thing I'm not showing on the slide is that, for example, when you compute electromagnetic correction to the charged pion mass, it is cut off at the compositeness scale in QCD, and it's supposed to come out finitely positive. If you do the calculation here, it also comes out finite, cut off by m, the SUSY breaking scale. So this intuition that SUSY breaking scale is providing the composite scale also seems to pan out by doing that kind of calculation. So all of these things are something you learn about QCD, where you arbitrarily cut off every integral because you're told to do so. But here, again, everything becomes calculable. So these states are established, and I told you this upside down spectrum. And these states are not QQ bar mesons, it turns out. they're believed to be either tetraquark or meso-meso molecule. And that sounds exotic, but that's the way we can understand this, because otherwise you can't explain the quantum numbers. And by doing the calculation I outlined before, you can work out what the spectrum looks like. So when you turn on the mass of the quarks, I told you already that the pseudoscalar mass squared goes linearly with quark mass. And this the scalar mass squared also goes linear with quark mass out of some common number to begin with. But I found this coefficient to be negative, which is about 2.7 times bigger than 2.2 times bigger than the other one. So C prime being negative really does show that spectrum is upside down. As quark mass is increased, the scalar masses come down. What comes out most is the state with the strange quark involved. What doesn't come down very much are the states that have the light quarks involved, and that's exactly the spectrum you get. So as I admitted already, I didn't expect this to work out so well, but as a bonus, it seems to work that well. So that's another evidence that near-SUSY limit and non-SUSY limit seem to be continuously connected. And so far, I only talked about rather few number of NF. And if you go to larger number of NF, you have to switch your description to meson bound states. And in this case, what you see is the supersymmetric potential is minimized at the origin, but with supersymmetry breaking is minimized where, again, meson acquires an expectation value showing chiral symmetry breaking. In this case, meson composite is expected to behave with the canonical theta potential, because we know the meson is the degree of freedom that matches to the anomaly and therefore can be interpreted as the dynamical fields. So as long as you are well below the dynamical scale, we can treat meson to be canonical, and then you can minimize the potential and go through the kind of phenomenology I talked about earlier.
Excuse me?
Yes.
So you skip the deformed moduli case. What happened with the baryon branch?
Yeah, I can come back.
Okay. Thanks.
And if you go up to even higher number of flavors, you have this dual magnetic theory, which is kind of weird. But once again, you can find the minimum where mesons acquire values, where you can integrate out these magnetic quarks that will lead to this, what is called the Gaussian condensate superpotential, and show again the potential to behave the way just similar to the previous slide and minimize the potential. So this is case-to-case question. In this case, unfortunately, we don't have the full solution to the theory. And that's because in this theory, these baryons, the meson fields, end up acquiring expectation values of the order of the dynamical scale. So we actually lose control over the Kata potential. Some people have already expressed the concerns about. So we don't fully understand it. Based on some naive dimensional analysis, the meson acquiring a wave seems to be the good minimum, but we cannot prove that that is the global minimum at the end of the day. So that's the limitation of our methodology. And if you go to even higher number of the number of fermions, it turns out that there is the direction where baryon number gets spontaneously broken. And when NF is bigger than 1.48 NC, unfortunately, this direction has a lower minimum than the minimum with the chiral symmetry breaking, which is only a local minimum. So that is there. But if you naively jack up the size of supersymmetry breaking, they seem to cross, and chiral symmetry breaking minimum seems to become the real minimum at the end of the day. But once again, we don't have full theoretical control over here. So this is meant to be only suggested. So what is going on here is that this local minimum does seem to be continuously connected to the chiral symmetry breaking in non-SUSY limit, even though there's a deeper minimum of the baryon number breaking for near-SUSY limit. They have to switch as SUSY breaking is increased, and that's a phase transition. So in this case, there is a phase transition, but local minimum can still tell us something useful in a non-SUSY limit. So if you believe in this continuity. So that's the picture. So for low number of flavors, as far as I can tell, there is no sign that near-SUSY limit is not continuously connected to non-SUSY limit. Everything seems to work out even better than we hoped for. For larger number of flavors, there is a phase transition, but you can still identify chiral symmetry breaking a local minimum, which seems to be continuously connected to non-SUSY limit, and hence we believe that non-SUSY limit would have chiral symmetry breaking all the way up to 3nc, and beyond which it may lead to the infrared fixed point. So that's the picture we came up with. And once you have the SUN gauge theory nailed down, I can ask the question about the confinement. So in SUN gauge theories, you can screen any other color charges with the quarks in the fundamental representation. So there's actually no precise notion of confinement, it turns out. The Wilson loop doesn't show the area law. But if you switch to SONC gauge theory, with the quarks transform under vector representation, there is a Z2 center of the group that cannot be screened by the dynamical quarks. So there is a rigorous definition of confinement in this theory. Then for SONC gauge theories, it turns out that there is actually a particular value of number of flavors where you see a Coulomb phase. And on this Coulomb phase, again, you have this moduli space where you have points where monopoles become massless. And again, because anomaly mediation is UV insensitive, you know exactly how SUSY breaking would appear on these monopole dione states and work out the solution. And it turns out that the minimum is where the dione condenses with this particular value. And because the dione condenses, which has the magnetic charges in them, then the confinement follows as a dual-Meissner effect, which Stanley Mandelstam told us a long time ago. And also, this point where diones condense, you have this U field, which is this determinant of the meson that has a particular value. Therefore, mesons condense at the same time as the diones, meaning the confinement and chiral symmetry breaking happen together. So you can see that as well. Finally, just 2 minutes, I apologize. Now that we have the framework all set up, I try to apply this kind of idea to chiral gauge theories where pretty much nothing is known. So standard model itself, the chiral gauge theory, it's a shame that we don't know what they do. We can simulate on the lattice. People have some guesses on what chiral theories might do, called the tumbling. And that's an idea that once the chiral gauge theory becomes strongly coupled, they try to form fermion bilinear condensates, which is not gauge invariant. So gauge group ends up breaking its own gauge symmetry and breaks down to smaller gauge group. Then that gauge group would lead to another fermion bilinear condensate, which further breaks gauge invariance until the point that theory becomes a vector-like, which may undergo chiral symmetry breaking. Weird idea, but that's the only idea we used to have. And so if you apply this idea to SUNF gauge theory, the antisymmetric tensor, and certain number of fundamentals, this argument will tell you this gauge non-invariant condensating form that will break SUNC gauge theory to SU focus SUN-C-4. And there's a further breaking going on. In the end, theory becomes vector-like, and they would predict that you have massless fermion composite states. That's the guess people came up with. But now that we do have explicit solutions, and the simplest solution you can say is about SO10 with several 16s. You can write down again non-perturbative effects. You break supersymmetry, then you can work out what kind of symmetry breaking you get. And here you don't get any global symmetry breaking, which is not consistent with the tumbling hypothesis. So here you have a clear discrimination between this tumbling hypothesis as the guess of non-SUSY gauge theory versus exact results you can get near SUSY limit. They suggest different patterns of symmetry breaking. So one of them actually has to be wrong in a non-SUSY limit. Right now, we don't have a clear way of deciding which. So that will be a very interesting question for the future study in lattice gauge theory.
Well,
That's your exhibition.
I don't know.
So this is the end of the talk. So this is the summary of all the chiral gauge theories we have studied so far, including SUN gauge theories, E6, SO10. In the vast majority of the cases, tumbling and SUSY results are different. So we will see which one is right, but at least the SUSY results are meant to be exact results as long as supersymmetry breaking is small, so that we could already use them to write down, for example, theory of supersymmetric composite axion, because you understand exact solutions for that. So this kind of solution may or may not be consistent with the non-SUSY limit. I don't know that yet, but at least they are useful enough that you can use them for model building purposes. So what kind of model building I can anticipate? Well, massless composite fermions, light composite scalars, I mentioned this already for the sigma particle, new symmetry breaking patterns you wouldn't have expected from tumbling hypothesis, and all of them are now at our disposal to write down theories of beyond the standard model physics using supersymmetric limit. And so they are testable predictions on dynamics. So we will see how we end up deciding what prediction turns out to be the correct one. So let me conclude. So we wanted to understand the real cow. It turns out that SUSY plus anomaly mediation seems to be very useful. So that's a spherical cow, but you break supersymmetry a little bit. You do pick up features that look very much like what we expect in QCD. I have shown a bunch of circumstantial evidence for that. And results turned out to be consistent with what we expected, going back to Nambu and Yukawa. No obvious sign of phase transitions, at least for the small number of flavors. And we can apply this to systems not understood yet, including chiral gauge theories. And in particular, this should be also applicable to lower dimensional systems that might be useful for strongly correlated condensed matter physics. And I haven't tried that at all, but something I'd like to think about. So, and maybe this is the way we understand dark sector as well. Okay, that's it. Thank you.
All right, so any questions for?
Jeff.
Is there something special about anomaly mediated supersymmetry breaking? Can I change the supersymmetry breaking scheme and still get, like, still match QCD?
So if you do things like gaugino mediation or gauge mediation, you don't know how they would appear in IR physics because they are not controlled by the external symmetries. You can put them into UV Lagrangian, but you don't know what you get out in the IR. You want RD term? You do, but it doesn't generate gaugino map. So the anomaly mediation turns out to be the minimum choice that achieves two requirements. Both gaugino and squawks become massive in UV, and you know how they appear in IR.
Okay, so makes sense.
I hope you're happier now.
Are we ever gonna learn anything about the conformal window from any method like this, the non-supersymmetric?
So what I said is the best I can come up with. So in a conformal window in the SUSY limit, once you turn on supersymmetry breaking, they seem to go to chiral symmetry breaking. This is not the conformal.
I see. This is
So
true
that's
for
why.
any gauge group? it
Right,
seems?
right. Yeah, we looked at SO and SPN.
And what if you keep some of the, you might imagine not making all the scalars massive at the same time?
Then that's a different story. So you have to go to a different scheme of SUSY breaking. You may get different answers in that case. But then it's not a non-SUSY limit of the theory either. Right? Because you may keeping some gauginos and some squawks light. Any other questions? I already lost half of the audience.
Well, there is a colloquium in
Oh, I see.
10 minutes.
Well, then I will have to.
Wendy Friedman is talking.
That's it? Okay, thank you. Makes sense?
In terms of
Yeah.